So probably many of you know that the first Hell lecture was given by Genevieve in Atlanta 3 years ago. And she was talking about global structural stability properties of infinite-dimensional semi-flows, mainly those defined by parabolic hyperbolic equations, Kupka-Smale, Morse-Smale properties. One of the fundamental papers in that area is this paper by Dan Henry, where he considers one-dimensional parabolic problems on bounded intervals, and he proved that the stable and unstable manifolds of equilibria intersect transversally always, okay? Not just generically, but automatically. So I want to read a quote from that paper. This is what Henry writes on the second page of the paper in the introduction. He says, "This was the view of Jack Hale in 1981. It is the belief of the author that the transversal intersection property always holds. The recent results of Matano could play a role in the proof. Once again, he was right." Okay, so that's what Henry says. This paper, quote is in Henry's paper is an overview paper by Jack Hale. He quoted it in the preprint form, but later it appeared in this lecture notes volume. It's an overview paper about infinite-dimensional dynamical systems. And here is what he wrote about this particular problem. Okay, so I think this quote is a very good example and illustration of how Jack influenced this area of dynamical systems. Okay, so it tells us several interesting things. First of all, Jack had great vision. Okay, so this is an excellent example of that. The theorem, which he correctly guessed to be true, was really a fundamental result in the area. It stimulated a lot of research later on. He also had great intuition because he correctly guessed the tool for the proof. These results of Matano, which, by the way, I will specify later in this talk. It also tells us how generous Jack was. Okay, so he knew the theorem, the right theorem. He knew the way to prove it. Yet he didn't mind to share it with everybody else. Okay, so he was like that. And also it tells us that he was right most of the time. Mostly. Not always. All right, so that's a really good example. I personally have benefited a lot of the vision and generosity of Jack. Even a long time before I met him, which was in Minnesota in 1989, I read several of his overview papers, like the one quoted here, where Jack, he was so enthusiastic about the research. He wrote several interesting things, and each time I read one of those papers, I wanted to prove a theorem. Didn't always know which theorem, but just wanted to prove something because it was very contagious what Jack wrote. So it's really a great honor for me to be giving this lecture in Jack Hale's memory. Okay, so as I said, the results of Matano or these Sturmian zero-number properties will play an important role in these lectures, in the two lectures, as they do in perhaps fair to say that in most qualitative results in one-dimensional parabolic equations, the zero number properties are used in an essential way. Okay, so the problem we will be discussing is this one-dimensional parabolic equation on the real line. The nonlinearity is either C1 or at least locally Lipschitz. The initial condition is just the bounded function. You can take it continuous just to be nicer. And what I want to understand is the large time behavior, the asymptotic behavior of bounded solutions. Okay, when I say bounded, I just mean that the function u as a function of x and t is a bounded function on the real line across the maximal existence interval. And boundedness implies that the solution is actually global, it's defined for all time. So the large time behavior here means the behavior as time goes to infinity. Okay? So there is no blow up in this lecture, just bounded solutions. Okay, so let me give you, first of all, for the sake of background, some results on bounded intervals. Okay, so we consider some standard boundary conditions, Dirichlet, Neumann, or Robin, or periodic boundary conditions. And it is known then that all bounded solutions are convergent. Okay, so as t goes to infinity, they converge to an equilibrium. Each such solution converges uniformly with respect to x to an equilibrium. That's for separated boundary conditions, a result of Zeleniak, a different result by Matano, and for periodic boundary conditions, Chen and Matano proved the convergence. Okay, by the way, for separated boundary conditions, the convergence is also valid for the more general equation when we include the gradient term. For periodic boundary conditions, it's a little different. We already have periodic solutions in this case. I'm not going to discuss that case. Now, okay, so these are convergence results. Much more is known about the one-dimensional problems, in particular about the global issues, like the ones discussed in the paper by Dan Henry, which I mentioned earlier. The result was independently proved by Sigurd Angenent. Okay, so these are results about structural stability properties of the semi-flow. A recent paper, relatively recent in that area, is by our organizers here, Romain and Geneviève. Now, thanks to many papers by Henry, Brunowski, Fiedler, Rocha, and Wolfram, the dynamics on the attractor, okay, so assuming that the equation has some dissipativity properties, we have an attractor, then the attractor has been understood. Not just in a set, but even the dynamics on the attractor has been studied in detail. Okay, so these contributions include in particular a beautiful theorem by Carlos and Bernard, which classifies the dynamics on the attractor in terms of objects as simple as permutations. Okay, but in this lecture, I'm not going to discuss the global dynamics. I only want to talk about the behavior of individual trajectories. Okay, but on the real line, unbounded interval. Okay, so when we go to the unbounded interval, we immediately find solutions which are different from anything what we see on bounded intervals, namely traveling waves. Okay, so a traveling wave or a front, in this case, is a solution of this specific form. So it's one profile function decreasing, and this profile travels with the constant speed in one direction, okay, to the right in this picture. So assuming that c is different from 0, this function keeps moving with a constant speed, so it's not converging to any equilibrium. Okay, so when you look at this function globally, it does not converge to anything as t goes to infinity. Okay, on the other hand, when you look at this function just in bounded intervals, okay, so say you are a stationary observer, you can only see bounded intervals, possibly large, but just bounded. Then eventually what you will see, a part of the solution is that it converges to a constant steady state, right? The limit of this decreasing function at negative infinity. That's what you eventually see. Okay, so this happens with traveling waves and also more complicated solutions that when you look at them just in compact regions, bounded intervals, you just see very simple behavior, convergence to a constant equilibrium. Okay, so it is reasonable when we have unbounded intervals to look at the solutions from two different points of view. In one, you look at the solution globally, at large time. In the other, you take the point of view of a stationary or lazy observer and just look at the solution and what it does in the compact intervals. Okay, so I'll take both these points of view, but today just the first one, the point of view of lazy observer. I mean, jet-lagged people should be entitled for some laziness. Right? So that's what we'll do today. All right, so the basic question in view of what I said here about traveling waves is whether all solutions, all bounded solutions, when we look at them in the topology of the locally uniform convergence, whether they all converge to a steady state. Okay, so there is an offhand question which is very easy to answer. While there are several convergence results for solutions of these equations under various conditions on the nonlinearity and the initial condition, okay, so I quoted some of them here. The convergence is not true in general, even in the simplest equation, the linear heat equation. And this was observed a long time ago by Collet and Ekman, who constructed an initial condition which gives a solution which oscillates between two constant steady states, -1 and 1. Okay, so the initial condition looks like this. It's essentially a step function. Okay, so the initial condition is equal to either 1 or -1 on large intervals with sharp transitions between these values. And if you choose, if you space these intervals suitably, you get a solution which oscillates between -1 and 1, or in other words, these two constants, -1 and 1, are in the limit set of the omega of the solution, the omega limit set of the solution. Okay, so along some sequences of times, the solution converges to each of these equilibria. Now, it can be shown that although the solution is not convergent, it is quasi-convergent in the sense that the omega limit set consists of steady states. Okay, so I take here the omega limit set with respect to the locally uniform convergence. Okay, so the usual definition, just with the convergence, just locally uniform on each compact interval. Okay, so I use this definition of the omega limit set today for nonlinear equations, and also this concept of quasi-convergence I will also use for nonlinear equations. Okay, so it means that the omega limit set of a solution consists of steady states of the underlying equation. Now, in the case of the linear equation, it's very easy to prove that we have a quasi-convergence. Namely, you take the omega limit set. Okay, so it is well-known invariance principle that the omega limit set consists of entire solutions, solutions which are defined for all times, positive and negative. The original solution is bounded, therefore the omega limit set consists of bounded entire solutions. And in the linear heat equation, all bounded entire solutions are constant. That's the Liouville theorem for caloric functions or solutions of the linear heat equation. Okay, so in this case, all points in the limit sets are actually constant steady states. All right, so here we have now a more reasonable question to ask, whether even for nonlinear equations, all solutions are quasi-convergent. Okay, now when you think about quasi-convergent solutions, they are not convergent, but it's not like oscillating solutions which would converge to a periodic solution. Right? The oscillations slow down as t goes to infinity. Actually, for quasi-convergent solutions, the time derivative converges to zero locally uniformly on R. Okay, so in some sense, numerically, you cannot distinguish from convergent and quasi-convergent solutions, or less it's difficult to distinguish. The solutions which are in the energy space, in the sense that the usual energy functional stays bounded along those solutions. For those solutions, we get quasi-convergence immediately, right, from the existence of the Lyapunov functional. But the emphasis here is, or the focus of these lectures is on solutions which are not in the energy space, just any bounded solutions. Okay, so I want to give you two answers to the question. The first one is no. So in general, the solutions are not necessarily quasi-convergent. And then I'll give you a result, or two results actually, in which I'll identify classes of initial conditions which give quasi-convergent solutions. Okay, so for the first answer, I want to give you examples. And I also want to understand what we have in the omega limit set if there is something more than just steady states. Okay? The omega limit set does not consist of steady states. What is in there? What kind of entire solutions can we expect to appear there? Okay, so the omega limit set cannot be completely arbitrary. Okay? It's a connected set. It consists of entire solutions. More importantly, there are results of Galay and Sliepchevich, both in the audience, Thierry and Sinisha, who proved that the omega limit set always contains at least one equilibrium. Okay. By the way, this is a result which is also true in dimension 2 for this type of equations, and it's not known whether it's true in higher dimensions or not. Okay, so at least one equilibrium is always there. Yeah, now the first evidence of the existence of non-quasi-convergent solutions is in this paper by Ekman and Rochemont, who considered the equation with this cubic bistable nonlinearity. And the initial condition is again as in the example which I gave you for the linear heat equation. Okay, so essentially the step function with values at -1, taking values -1 and 1 on large intervals and sharp transitions between them. You take infinitely many transitions or kinks. Okay, so in this paper they studied the annihilation of pairs of kinks of the solution. Okay, so if you need to choose these intervals suitably, and then what happens is that the solution will indefinitely oscillate between -1 and 1. Okay, so the step function gets smoothed out immediately. And then what happens is that the solution starts to annihilate pairs of kinks like these two. Okay, so they travel toward each other and annihilate each other. So the solution then is very flat, close to 1 in large interval. Then the next pair of kinks come in, move toward the origin and annihilate each other. The solution is now flat, close to -1 on large interval. And then this is repeated infinitely many times. Okay, so it can be proved. So you see here, just like in the heat equation, the solution has -1 and 1 in its omega limit set. But the difference now is that as it goes from one constant to the other, it is not flat. It is not close to a constant. That can be proved. It can be proved. Ekman and Rochma did not do it in their paper because that was not the focus of their paper. They didn't study quasi-convergence. But it can actually be proved that the omega limit set of this solution contains the constants, -1 and 1, and some solutions which are not steady states of the equation. Okay, so the solution is not quasi-convergent. Now, when you want to understand what kind of entire solution appears in, or can appear in the omega limit set of such a solution, and it definitely, for some, I'm not saying that this is what happens for all initial data which produce such a solution, but at least for some initial data, one can prove that the following entire solution is contained in the omega limit set. Okay, so it's an entire solution which has just 2 kinks. As time goes to -infinity, okay, so it's an entire solution, it's defined for all times. As time goes to -infinity, those 2 kinks go to minus and plus infinity, so they disappear. As time increases, okay, so we do not see them here in this picture because they are far out, but they start to move in. They move in, annihilate each other, and eventually we see something very close to the other constant steady state, -1. Such an entire solution was constructed and further studied by Chen, Guo, and Ninomiya. This is Shin-Fu Chen. Among other things, they proved the uniqueness of such solutions up to translations. And since all right, so one more thing about this solution is that when you now look at it at, say, any fixed point x in space. Let's see what it does as time goes from -infinity to infinity. Okay, so the function is decreasing with respect to time. So it goes from 1 to -1. So you can actually view this solution as a heteroclinic solution in the infinite dimensional space between the 2 constant steady states, -1 and 1. And since for this nonlinearity there is really no difference between -1 and 1, okay, they are equally stable, so to speak, we also have such a heteroclinic in the opposite direction. All right, so we have a heteroclinic loop in the omega limit set for this solution in the infinite dimensional state space. Okay, so there are some natural questions in connection with the example I've just given you. The first one is that the initial condition has these large oscillations. Okay, so the amplitude of the oscillations is bounded away from 0. So the question is whether this is really necessary. Okay, so whether for nicer initial data, say initial data which have limits at -infinity and infinity, this is different. Or even when we take initial data whose limits at negative infinity and infinity are equal. Like this space here is the space of continuous functions whose limit at negative infinity and infinity is 0. Okay? So what happens to such solutions? And the other question is that the nonlinearity in this example is very special. I mean, the very specific form of the nonlinearity is not so important. What is important that it is a bistable, balanced nonlinearity, because it has these two stable constant steady states, unique 0, unstable steady state between them, and the integral from one constant, stable constant to the other is equal to 0. This is what I mean by balanced. Okay, so when I say unbalanced, this integral will be different from 0. Okay, so this is definitely not a robust class of nonlinearities. Okay, so one can speculate now that perhaps non-quasi-convergence is something very exceptional for robust nonlinearities. This does not occur. So is this true or not? Okay, so what happens in the generic case? All right, so to address those questions, I constructed a couple of other examples, more than a couple, 3 actually, but I'll mention just 2. Okay, so the first one is still for balanced bistable nonlinearity. And the non-quasi-convergent solution is very similar to the previous example. Okay, also the scenario how it oscillates between -1 and 1 is very similar, except that the oscillations are not large here. Okay, so it's a function in a C0R, the initial condition is. So the point is, okay, so in this example I realized that for the previous thing to happen, one does not really have to consider large kinks. Okay, so the initial condition is still flat on large intervals, but the value is not large. It decays to 0 as x goes to negative infinity or positive infinity. Okay, so what happens here is that the kinks first develop before they actually annihilate each other. Now the other example is for an unbalanced bistable nonlinearity. Okay, so this is a robust example. This is to address the other question I had before about the specific nonlinearities. Okay, so the example is a solution whose omega limit set contains one of the stable constants, -1, and a ground state at level -1. A ground state is a function which looks like this. So it's in the unbalanced bistable nonlinearity, such a solution, such a steady state exists. Okay, it decays to -1 at positive and negative infinities. And there is a solution which has these two steady states in its omega limit set. And in addition, it has some functions in it, in the limit set, which are not steady states. So it's not a quasi-convergent solution. Now later I found a more involved but more useful construction where I showed that this can be achieved with the initial condition actually in C0R. Yes?
How sensitive is the first example to the initial?
In some sense, it's a robust. You can do it with respect to some weighted space. An open set of initial conditions gives you such a solution. Okay, so the second example can be done with again, an initial condition which is a limit at negative infinity and infinity equal to 0. Okay, so this tells us actually that non-quasi-convergent solutions appear very frequently in this type of equations. Each time you have a bistable interval, so you have a nonlinearity which is bistable in some interval, balanced and unbalanced, you do have non-quasi-convergent solutions. Okay, so it's not something you can get away from by a small perturbation of the nonlinearity. It's very frequent. Now let's think about entire solutions which appear in this example with the ground state in the omega limit set. It's quite interesting, actually. The entire solution which appears there. All right, so in the previous example, we had a heteroclinic loop in the omega limit set. Okay, so since the omega limit set is a chain recurrent, it's natural to expect that in this example where we have these two steady states, there is also something like a heteroclinic loop between them. Okay, so one way it's very easy actually. Okay, so when you want to go from the ground state down to -1, you can even find a heteroclinic solution in L infinity. Okay, so in L infinity you can do the usual linearization, unstable manifold. The ground state has Morse index 1. It has eigenvalue 0, the linearization due to translation invariance, but it also has a positive eigenvalue. Okay, so it has a one-dimensional unstable manifold. A part of that manifold is a trajectory decreasing in time, which connects the ground state and the constant steady state. Okay, so it's a heteroclinic even in the uniform topology, not just locally uniform. Now going the other way is kind of curious, right? Because now we want to go from -1, which is asymptotically stable, to the ground state, which is unstable. Okay, so the first ground, something like this should not be possible, but we must keep in mind that we want a heteroclinic not in the uniform topology, but in the locally uniform topology. That's where we are taking the omega limit sets. And such a thing exists. Okay, and it was constructed in our paper with Hiroshi Matano, which we are just completing. The solution looks like this. So it's an entire solution, again, defined for all times, which has two humps. Okay? The two humps, as time goes to -infinity, disappear. They go to -infinity or positive infinity in space. With increasing time, they move toward each other. Okay, and eventually they collide. And the final profile is a ground state. Okay, so the shapes of the two humps, each of them is that of the ground state again. So they look like a ground state for negative time, large negative time, but we have two of them. Eventually we have just one. Okay, so this is an interesting solution because the type of equations I'm looking at does not admit a traveling pulse solution, a solution with one pulse moving with a constant speed. It does not exist here. Okay, so we have here something like a traveling pulse solution, but the speed is not constant, of course. Okay, so the speed is very small for large negative times. Then the speed becomes larger, the humps accelerate a little bit, and then they collide and just form one hump solution. Okay, so that's the entire solution, which again can be proved to appear at least for some solutions in the omega limit set. You're doing good, right?
Yeah. 18 minutes. 18.
Right. 45. We finish at 40.
No, 45.
45? Sorry. Good. All right, so these were the examples. Now let me give you some theorems. I mean, the examples are theorems, right? But they are there to illustrate that something is possible, something exists. Here I want to now prove some general results about the large classes of initial data. Okay, so I will consider two types of initial data now. One is non-negative functions in C0R. And I take, in this case, f at 0 to be equal to 0, which makes this a good space for the equation to be well posed. Right? So it's an invariant space for the equation. You start in this space, you remain in that space if f at 0 is 0. The second class, which I'll mainly consider in the second lecture, is that of front-like solutions, typically studied in connection with traveling waves. And I will look at them from several points of view tomorrow. Okay, so let's consider now the same equation with initial data, which are continuous functions, vanishing at infinity and non-negative. Okay, so here is a theorem. It's a joint work with Hiroshi Matano, a different paper, which actually is it's about to appear. I have a preprint on my webpage if you are interested. Okay, so it says that the solution of this Cauchy problem is always quasi-convergent. The omega limit set consists of equilibria. And more specifically, each steady state in the omega limit set is either a constant in gamma. Gamma is a set which I will define in a second. Or it is a standing wave with the limits in gamma, or a ground state at some level gamma, in gamma. And moreover, all functions in the omega limit set belong to the same chain of this ODE. Okay, so this ODE is the steady state equation for the parabolic equation. All steady states solve this ODE. Okay, so this is what I consider here. So let me define the terminology used in the theorem. Okay, so first of all, this set gamma, which is used here. Okay, so it's the set of global left maximizers of the function capital F, the primitive of small f. Okay, so we take this function, capital F, and collect in the set gamma all critical points of capital F, which are global maximizers of f, but only to the left of themselves, okay, in the interval 0 gamma. So like in this picture, okay, global, not necessarily strict, but the left global maximizers of the function f. And notice that 0 is included in this set. All right, so that's the set gamma. Ground state is as before, except now it can be at a different level. Okay, so a ground state at level gamma is a solution of this ODE which has the limits at negative infinity and positive infinity equal to gamma, and it's greater than gamma. So I only consider ground state greater than the limit constant, not the other way, not below the constant. A standing wave is a traveling wave with speed equal to 0, but I only consider traveling fronts. Okay, so solutions of the ODE which are either decreasing or increasing, so they have limits. Okay, so I say a standing wave with the limits gamma minus, gamma plus is a solution of this form. It looks like this. Okay? It has these two limits, negative gamma minus, gamma plus. And finally, let me define the chain. used in the theorem. Okay, so for that we consider the first order Hamiltonian system corresponding to the second order ODE. Okay, so that's the system. And a chain is a maximal connected set in R2, in the state space of the system, consisting of equilibria, homoclinic orbits, and heteroclinic orbits of the system. Okay, so I have several dynamical systems here. I have the PDE, the parabolic equation. Here I have the Hamiltonian system in the plane. So all these orbits are orbits of the Hamiltonian in the plane. Okay, so that's the definition of the chain. An equivalent, a more useful definition for my purposes here is the following one. Okay, so a chain is a connected component of R2, the state space, from which you remove all closed orbits, all periodic orbits, non-stationary periodic orbits. This requires some modification of the nonlinearity near infinity. Okay, I'm assuming here that all solutions of this Hamiltonian system are global, bounded. Okay, so then a chain can be equivalently defined this way. Okay, so you remove all periodic non-stationary orbits. What remains is some set. You take a connected component of that set, and that's what I call a chain. Okay, so that's the terminology. Here is the theorem again. And so we want to show that all elements of the omega limit set, which are now functions, have these properties. Okay, so they are steady states characterized here, and I'll make more precise the statement that they belong to the same chain. Okay, so again, I emphasize that there is no use of a Lyapunov function here. The quasi-convergent quasi-convergence is proved completely differently. And the quasi-convergence theorem that we have here is also very useful when you want to prove the convergence for more specific initial data or more specific nonlinearities. For example, it can be used to prove that generically with respect to F, you have convergence if you take, again, the initial conditions, initial data in this space. Carlos?
So all chains include the equilibrium?
Not necessarily. No, they are connected components. Okay, so they might be away from zero. I mean, the omega limit set of a solution does not have to include zero, right? Because we are looking at the locally uniform convergence. So.
Can you say something about this set omega of U inside the chain? I guess it's connected, and is it recurrent or is it?
Yes, it is. That's a general property, right? That it's a connected set in the topological, actually it's a metric space in this case. Connected consists of entire solutions, and it's recurrence properties. But in this case, we see that it just consists of steady states, of equilibrium.
Yeah, but I mean, if you see it in the other diagram, so you have this diagram of the dynamics of the ODE, then you have heteroclinic points and so on, and a subset of that are the omega limit.
In some sense, yes, right? But remember that the way I view the omega limit set is a subset of the functional space of an infinite dimensional. But we will get to this point in a second. Okay, so here are the main tools of the proof. It's the zero number properties and spatial trajectories. So here is the zero number, the result mentioned at the beginning of this lecture. So it concerns solutions of this linear parabolic equation with a coefficient depending on x and time. Notice that when you take two solutions of the nonlinear equation by the mean value theorem, the difference satisfies such a linear equation. Now the zero number is simply the number of zeros of a given function. Okay, so we take a non-trivial solution of this linear equation. At each fixed time, we count the number of zeros, which is possibly infinite, and that's the zero number. Okay, so the function, the solution can start from some initial condition looking like this. But the property, one of the key properties, is that such intervals of zeros cannot appear at positive times. Okay, so here are the three main properties of this zero number functional. It is non-increasing in time. If you know that you happen to have a solution which near infinity is different from zero, okay, then the zero number becomes finite immediately. Start from such an initial condition as here. Okay, near infinity, it is does not vanish. At each positive time, the zero number is finite. And if you happen to have a time where the zero number is finite and you have a multiple zero or a degenerate zero, then the zero number drops at that time, in the sense that it is smaller after t0 than it is before t0. Okay, so this is the result, the origins of that, the first, at least, the monotonicity property goes back to Sturm, but Hiroshi Matano was the first one to use it in the qualitative studies of parabolic equations. So he gave a nice proof of this result also in a more general setting. The other properties, the dropping property in particular and the finiteness, are due to Sigurd Anhenent. Xu and Chen has a more general result and more precise result, and with him we also have a paper where we prove these sort of properties for multidimensional equations in the radial setting, radially symmetric solutions. Okay, there is also a version on bounded intervals with standard boundary conditions or this sort of boundary conditions. Okay, so if you block the zeros from entering or leaving an interval, then again you have these properties counting the zeros in the given interval only. Now notice that there is a useful consequence of the second result. Okay, so if you know that you have only finitely many zeros, the zero number is non-negative, so it can drop only finitely many times. So then you are guaranteed that for large times there is no more dropping, and therefore there is no more multiple zeros at any large time. The function must have only simple zeros. Okay, so that's the zero number. What are now spatial trajectories? Okay, so I take a solution of the nonlinear equation now. For any fixed time, I consider this set in the plane. Okay, so this is the pair U, and it's a spatial derivative parameterized by x. That's what I mean by a spatial trajectory of the solution at the given time t. Okay, so it's a subset of R2, the spatial trajectory. Looks like this. Okay, it's a curve in R2 for each fixed time. It starts and ends up at the origin because we are taking the initial data in C0, and it can be proved that also the derivative converges to 0 at positive times. Okay, so this is a spatial trajectory at some time, and now it evolves with time in some way. We want to understand how. Okay, if you take a steady state of the equation, then the spatial trajectory is, of course, independent of time, because the solution is, and it is a true trajectory of the Hamiltonian system corresponding to this OD. Okay, so that's the spatial trajectories. Now, how are these two things related, zero number and spatial trajectories? Okay, so imagine that we have a solution of our parabolic equation, and we have a periodic steady state of that equation. Okay, so a periodic steady state, when you consider its orbit in the phase plane, it's a closed orbit. Okay, so suppose that the spatial trajectory of our solution at some time intersects the trajectory of the periodic orbit. So look at the point of the intersection. Okay, so at this point, the values of u and u sub x for these two solutions coincide. Okay, so the derivative and u. So when you take the difference, so there is a periodic solution in that case, such that when you take the difference of that periodic solution and the solution u, time-dependent solution, at this time there is a multiple zero of this function. Okay, so that's how you see the intersection of spatial trajectories is related to the zero number, because we see multiple zeros. Okay, so in this case, when I took the periodic solution positive, I know that my solution is close to zero, near infinity. So I'm fine as the zero number property near infinity goes. Okay, so I know that one of the theorems applies in one of the properties. I have finite zero number, and I know that such a multiple zero cannot occur for large times. That was the corollary which I mentioned. Okay, so what we actually want to prove here is more than this, because there's some parameterization involved, so one has to consider different translations of the periodic orbit. But it can be proved actually that such tangency cannot occur for large time for any periodic solution, even when you consider solutions, periodic solutions which change sign. Right? So here I took a positive solution. We are dealing with positive solutions of the parabolic equations, but the periodic solution we consider here may change sign. Even so, one has to deal with infinite zero number necessarily, but it can be proved that tangency cannot occur for a large time. Okay, so in other words, we have the following conclusion. If we take any element of the omega limit set, okay, so that's something the solution goes to along a sequence of times, going to infinity. And we take any non-stationary periodic solution of the Hamiltonian system, then the spatial trajectory of the function phi does not intersect the trajectory of the periodic solution of the Hamiltonian. Okay? So these are now elements of R2. So it can be proved that we have such a conclusion. Okay, so now this comes to your question, because we can actually take all elements of the omega limit set and take their spatial trajectory. I guess that's what you were wondering about, right? So we get this connected set in the plane. Okay, so it's connected because it's coming from the omega limit set of some PDE solution, but it's a set in the plane. It is a connected set and does not intersect the trajectory of any periodic solution of the Hamiltonian system, any non-stationary periodic solution. Okay, so necessarily this set is contained in a chain, because remember I defined a chain equivalently as a connected component in R2 in the set which we obtain by removing all periodic solutions. So these are necessarily contained in such a chain. Okay, so this is what I meant actually in the theorem when I said that all elements of the omega limit set are contained in one chain. Okay, so this makes it precise. Actually, I was talking there about the spatial trajectories of functions in the omega limit set. Now, at this point, we don't know yet whether the elements of the omega limit set are steady states or not. That's what we still want to prove. Okay, so that requires additional arguments. So the next thing is, next step is to use a zero number again. This time we take any constant steady state psi and look at the zero number of the difference from other solution. And I omit the argument here. It can be proved that if you take again a function in the omega limit set, if it is not a constant steady state itself, then its spatial trajectory cannot contain the trajectory of a constant steady state. Remember, okay, so I take a constant steady state of the PDE, so it is psi is a zero of f, so psi, this pair psi zero is also a steady state of the Hamiltonian system. Okay, so if the function phi is not a constant steady state, its spatial trajectory cannot contain the trajectory of a constant steady state. That's what this conclusion says. Okay, so what we know now, we take the spatial trajectory of such an element phi. It's a connected set. It is contained in a chain. That's what we know by the previous conclusion. But if it is not a steady state, a constant steady state, it is also contained in the chain from which we remove the trajectories of constant steady states. Okay, so like here, this is a chain. We remove these steady states, and what remains is a union of trajectories of the Hamiltonian system. Okay, so this connected set must actually be contained in one of those, one of the trajectories of single solutions of the Hamiltonian system. And that can be used to prove that it has to be a steady state. It's a PDE argument, again, using unique continuation type results. Okay, so phi is actually a steady state. And this gives us the conclusion that we wanted to prove. You see the functions in the omega limit set are contained in a chain. Each of them is either a constant steady state, or it's given by either a homoclinic or heteroclinic of the Hamiltonian, which corresponds to standing waves or ground states. Okay, so that's the result. Right, so that's the end of the sketch of the proof of the theorem. Let me tell you what I want to do tomorrow. Okay, so we'll look at front-like solutions. So those will, a subclass of that is the solutions which have the limits different at negative infinity and infinity. I want to look at the quasi-convergent of such solutions, but also I want to look at, I want to take the other approach to the solution, the more global approach. Okay? Understanding the solutions, not just in the locally uniform topology, but everywhere. And that's where traveling fronts become very important. I have not used traveling waves in this lecture at all. They will be very important next time. All right. Thank you for your attention.